Alright, in this second video, we'll dive into the details of our RabbitMQ and our worker deployments. So let's get started. First things first, we'll take a look at our RabbitMQ.yaml file. I've made some changes to the labels from the last video to better clarify what some of the fields are doing. So inside this file, there are two Kubernetes resources separated by the triple dash line in line 23. The first object is a deployment resource, and the second one is a service resource. Deployment object is a higher level Kubernetes resource that manages replica sets, which in turn manages pods. Pods represent the atomic unit of work in a Kubernetes cluster. Itself can comprise of one or more containers. Pods are usually ephemeral in nature, meaning that they can go away due to reasons like migration or node failure. In order to maintain uptime, pods are usually managed by a higher level resource like deployment or replica sets. These higher level resources combine the pod creation and the desired number of replicas into a single unifying API. Let's first look at the pod creation API. In our deployment specs, the field under the template specifies how the pod is going to be created. For example, all of the pod created by our deployment will have the label app equals param tuning and type equals message queue pod. Type in the command kubectl get PO that's show labels to show the pods. You can see that our labels will correctly matches the YAML file. So you might have noticed there are two metadata fields in the deployment spec. The first metadata applies to the deployment itself, while the one inside the template applies to the pods. If you type the command kubectl get deploy -- show labels, it will show the labels for our deployment, and as expected, they correspond to the first metadata field. An easy way to remember this behavior is just to remember that template and only template applies to the pods created by the deployment, while everything else applies to the deployment itself. Inside our pod, we're creating one container by pulling the image RabbitMQ:3 management and naming it RabbitMQ container. We're also opening two ports, 567.2, which is the default port for communicating with RabbitMQ, and 15672, which is the management port with the UI. Node selector means that the pod will only be scheduled to the nodes that are part of the pool name default-pool. That completes our pod creation part of the YAML file. Now let's look at the two fields that act on the pods that we just created. The first one is the selector field, which defines how the deployment finds which pods to manage. In this case, we're simply selecting the label that is defined in the pod template. The replica field indicates how many copies of the pod will be running. Here we only have one copy. Next, let's take a look at our service object. A service is a way to expose an application running on a set of pods as a single network service. Since our workers and message queues do not share a network space, without service, our workers won't be able to communicate with our message queues. Service objects are relatively easy to create. There are only two key parts. One of them being the selector field. This field means that all the pods with the selected label will be part of this service. The label here must match the label that we assign to our pods inside the template field. Next, we see two ports associated with this service. This means that any traffic we send to RabbitMQ service at port 5672 would be forwarded to the pods port of 5672. Target port must match the container port, but we can change the port field. For example, if we change the port to 6000, then our RabbitMQ service will be available at rabbit-service:6000. And any traffic to that URL will be forwarded to the pod's 5672 port. There are multiple ways to validate if the service resource is correctly connected to our pods. You can create a temporary pod inside the cluster to curl or ping the service to see if it is up and running, or you can check if the endpoints are connected to the right pods. Here I'll show the second method, but for a more comprehensive debugging guide, I linked a document called Debugging Services from the Kubernetes official website in the description. So let's first run the command kubectl get PO-o =y to get the IP of the pod. Next, we'll run kubectl get endpoints, followed by our service name, which is RabbitMQ-service. To get the this will get the endpoints of the service. So the IP address here should match the pod's IP, meaning that the service is sending the data to the correct pod. And now let's take a look at our workers.yaml file. Remember, our workers is a Python program that reads messages from our message queue and does some processing and save the result to a MongoDB database. In order to run our workers, we must first create a container image. I'm not going to go over how to create that, but if you're interested, the code and the Docker file are inside the workers folder. Once you build an image, you can push it to any public or private Docker registries and configure Kubernetes to pull from them. By default, Kubernetes pulls public images from Docker Hub. I do want to point out one thing that in the code, which will lead into our discussion of the YAML file. So let's look at our workers.py file, and we'll see that our worker is trying to connect to a message queue using a environmental variable called secret URL. This environmental variable is coming from the config map resource called proc-config. Config map is a Kubernetes resource that provides key value pair storage that can be used to configure containers before they start. In our example, our worker pod reads the secret URL value from the config map, which matches to the service that we created in the RabbitMQ YAML file. Of course, we can hardcode the RabbitMQ-service address inside of our code, but that would make it a lot harder for us to reuse the container image. So next, unlike our RabbitMQ deployment, we specified the amount of CPU and RAM our workers are allowed to consume. We specify both requests and the limits for the resource, meaning that the container will be guaranteed 1 CPU core and 750 megabytes of RAM. Finally, the workers are deployed to a pool called pool-1 as opposed to the default pool for our RabbitMQ service. If we take a look at my GCP project, we can see that the two pools utilize different machine types, and that pool 1 utilizes GCP's preemptive nodes to save on the cost. If the node fails during training run, the pods will die and the training task will be returned to the queue, meaning that it really won't affect our overall system. However, if you think about it, if the message queue or the database goes down, it'll definitely bring the whole system down. That's why we don't put those two systems on the preemptive nodes. This completes part 2 of our video series, and in the next video, which is the last one, we'll look at how to deploy the MongoDB database.